Good day, everybody. In Chapter 15, we discussed many aspects of acids and bases. For example, we talked about quantitatively how to calculate the pH for a wide range of species. For example, we learned how to do the pH for first a strong acid. We also learned how to do the pH calculation for a strong base. Next, we talked about the pH calculation for a weak acid. Then we talked about the pH calculation for a weak base. For the strong acid pH calculation, the key is the hydronium concentration is the same as the original acid concentration because a strong acid will 100% ionize. A strong base, for example, calculate the pH for 0.1 molar of CaOH. Then you would be able to figure out the OH concentration is 0.2 molar. So you'll be able to figure out the POH, then pH. For the strong acid, for example, 0.1 molar HCl, you would know the hydronium ion or simply proton concentration will be the same as the original. So the pH will be negative log 0.1. This gives you 1. For a weak acid, you will need to write the equilibrium for a generic weak acid. Then use ice table. For more details, please refer to the previous chapter. For a weak base, you also build an ice table to begin with. But do remember, base reacting with water to produce hydroxide. So in this chapter, we're going to introduce to you a new type of pH calculation, which is the pH calculation for pH buffers. So what is a pH buffer? A pH buffer is a mixture that resists the pH change when a small amount of acids or bases are added to the system. A pH buffer typically contains a weak acid and a conjugate base, or a weak base and its conjugate acid. For example, these are some of the good examples of a buffer. A weak acid like hydrofluoric acid and the anion. In reality though, the anion will be provided in the form of salt, for example, sodium fluoride. For the weak base like ammonia, it can be combined with the corresponding conjugate acid. Similarly, ammonium ion is provided in reality in the form of salt, for example, ammonium chloride, etc. Okay. We have some other different ways to make buffers, which we will go over in a little bit. So how do buffers work? In the buffer system, okay, you will have a weak acid and the conjugate base, or you have a base with the conjugate acid, vice versa. What happens is when you add a base to it, it will react with the acid component. Do remember, a buffer is a conjugate acid-base pair, but it's weak conjugate acid-base pair. When the base is acid, for example, NaOH is added to the system, it's going to react with the HA, or the acid component of the buffer. After the reaction, do remember, the same amount of conjugate base is generated. Remember, when you consume certain amount of acid component, at the same time, the same amount of the base is generated. Similarly, with an acid, for example, hydronium ion, in the form of hydronium ion, is being added, it will react with the weak base component, or the A- component. Okay, same way, that's the buffer HA and A-, the conjugate acid-base pair. It's the weak conjugate acid-base pair. The acid that's being added will react with the weak base component of the conjugate acid-base pair. Do remember, when you consume some of the A- or the weak base component, at the same time, the weak acid, some weak acid of the same amount will be generated. Now let's talk about how to make pH buffers. In the previous slides, we already talked about you can directly mix the weak acid with the conjugate base in the form of salt. Or you have a weak base, then mix it up with the salt, which provides the conjugate acid. Okay, so that's the first two different methods to make a buffer. As we can see, in method number one, you directly mix a weak acid and its conjugate base. For example, you mix up certain amount of weak acid, HF, with the same amount of conjugate base, which is provided by the salt NaF. This provides the conjugate base, F-. The second method, you can directly mix a weak base, like ammonia, with the ammonium ion, which is the conjugate base, provided by, which is the conjugate acid, provided by ammonium chloride. Okay, this provides the conjugate acid. Okay, so the first one is the HF with F-. Second one is NH3 with NH4 plus. Okay. The third method is we indirectly make both components. For example, if you mix a weak acid with lesser amount of NaOH, do remember, in this process, for example, you have a 20 milliliter of 0.1 mole of hydrofluoric acid. If you mix with the less amount of NaOH, remember, NaOH will react with HF. Okay, since we have a less amount, so some of the HF is being converted to NaF and water as well. Do remember, not all hydrofluoric acid is converted, but the portion that is reacting with NaOH, at the same time, it will generate sodium fluoride, NaF. And in other words, the part of hydrofluoric acid that is consumed is being converted to the salt, which provides the conjugated base. Okay, plus the original amount of hydrofluoric acid that is not consumed. So you will have the conjugate acid and base pair. So this will also provide a third method to make a buffer. The fourth method is very similar. You started with the weak base, then you reacted with a small amount of strong acid like HCl. Okay. For example, you have 20 milliliter of ammonia, which is a weak base. You mix it up with the less amount of HCl. So what happens is NH3 will react with HCl, which will generate ammonium chloride. Okay, so some of this ammonia is consumed. Do remember, at the same time, it generates ammonium, which is part of this salt ester product. Okay, so the remaining ammonia with the newly generated ammonium ion, NH4 plus, is giving you a pH buffer. So to summarize this, we have 4 different ways to make a pH buffer. You can directly mix the weak acid with this conjugate base, or mix the base with the conjugate acid. Or you start with a weak acid, you react with smaller amount of NaOH, which means not all starting weak acid is reacted. You can also mix up a weak base with a smaller amount of strong acid like HCl. After you mix these up, you have a pH buffer. You will be able to calculate the pHs for these pH buffers. Okay. One of the key features for a pH buffer is, as I mentioned, you always have both the conjugate acid. Do remember, that's weak conjugate acid. Okay. And at the same time, you also have the weak conjugate base. You always have both the acid and conjugate base components. Both are weak though. Okay, that's the first feature. You can actually calculate the pH according to full procedure that is listed in your problem set. You can look at the details over there. After you set up the rice table, or so-called ice table, you will be able to find out the pH for a buffer is equal to the pKa plus the log of the conjugate base. This is the conjugate base, not just any base. Okay, it's the conjugate base. Similarly, that's conjugate base, not any base that you're adding, right? It's the ratio of the concentration of the conjugate base over that of the conjugate acid. So the denominator is the conjugate acid, not any acid. Okay, that's really, really important. A couple of things I want to emphasize in this Henderson-Hasselbalch equation, which you use to calculate the pH of a pH buffer. Do you remember? First, you always use pKa. If you started with a weak base, for example, if you have, even if you have a buffer like this, which has a weak base, and here the Kb usually is provided. Even if so, you still need to use pKa in the calculation. So what you will need to do is you calculate the Ka first, then you calculate the pKa, okay, for this type of calculation. So first, always use pKa. The second, it's always the conjugate weak base over acid ratio. The third thing is, I'm going to show you, because you do know the concentration or molarity. Your molarity is always the mole. I'm going to use N times the M for A minus divided by volume. Okay, moles divided by volume, that gives you the concentration. So for HA, the concentration will be the moles of HA divided by the same volume, because both species coexist in the same solution, so the volume is the same. So if we divide the top by the bottom, have you noticed the V is cancelled out? What this tells you is the ratio, concentration ratio, is exactly the same as the molar ratio. Okay. In other words, you can rewrite the Henderson-Hasselbalch equation in this way: pH equals pKa plus log the molar ratio, Na minus, divided by NHA. So the concentration ratio can be replaced with the molar ratio, and the Henderson-Hasselbalch equation will be totally valid. Now let's look at some details about how to use Henderson-Hasselbalch equation. When you look at the Henderson-Hasselbalch equation, which is listed over here, apparently if the base component is more concentrated than the acid component, you will know the log of the base over acid will be greater than 0. In other words, you will expect to see pH is greater than pKa. That's easy to understand, okay? Because when we have equal amount of acid and base components, okay, do remember the log would be, this would be log 1. Log 1 is 0. Okay, log 1 is 0. So pH, if this is 0, now would be pH equals pKa. In other words, when you have an equal amount of conjugated acid and the base in concentrations or moles, pH will be the same as pKa. If you have greater amount of a base component, that means your pH for the buffer will be higher or more basic. It will be higher than pKa. Okay, so if you have a less amount of a base component, you expect the pH to be lower than when the concentrations of acid base is the same, which is pH is the same as pKa when you have the same amount of acid and base. Okay, all right. So do remember the opposite is also true. For example, if you have a pH buffer, okay, and you see, let's say, if you have a pH buffer, let me erase everything over here. So if you have a pH buffer and the pH, okay, the pH for that solution, if pH for that solution is greater than pKa, then you can go back and draw the conclusion you expect that you have more base component than acid component in that pH buffer. Similarly, if you have a solution that has a pH that is equal to pKa, then for that buffer solution that exists in this very solution, you would expect they have equal amount of conjugate base and acid. Okay. If you have a pH for a certain solution smaller than the pKa for a conjugate acid-base pair, then you would expect the concentration for the conjugate acid-base pair is you have less base component than that of the acid component. So let's see how we use this detailed analysis. So given the pKa for nicotinic acid, okay, you don't need to know the specific formula, but it tells you the pKa for a certain acid is 4.85. What is true about the composition of a solution of this acid and its conjugate base? Remember, if you have an acid existing in water, it's going to ionize in a certain way, depending on pH of the solution. In this particular case, if you exist in pH of 4, you do remember, in this case, you will always have the acid and the conjugate base coexisting, okay? But in what ratio or relative concentration for this acid and the conjugate base? It would depend on how pH of the solution compares to the pKa of that acid. In this case, you do know your pH is 4, which is smaller than the pKa. pH is smaller than pKa. Or in another word, your pH is more acidic than when you have equal amount of acid and the conjugate base, which will give you pH equal to pKa. In another word, this solution is more acidic. In another word, when you go back, if it's more acidic, okay, you would expect to have larger amount of acid than that of the base. So more specifically in this example, you would have larger amount of acid than the corresponding conjugate base. The reason is because your pKa is greater than pH, or pH is smaller than pKa. All right, let's do another example. This example will be the simple calculation using Henderson-Hasselbalch equation. Calculate the pH for a solution containing 0.22 molar acetic acid and 0.13 molar sodium acetate. So when you look at this situation, first you got to recognize this is a buffer, because inside this mixture you have acetic acid. This is the weak acid. You can write HA, okay? That's the weak acid. Of course, if you really want to write the formula, we do know it would be HC2H3O2, okay? But we simply just use HA to represent it. The sodium acetate, we can simply write, because this salt represents, we can represent it as NaA, okay? So what this provides is the A minus, or the weak base component for this pH buffer. So in other words, you should be able to recognize this is a pH buffer. If it's a pH buffer, you will be able to calculate the pH using Henderson-Hasselbalch equation. That's what we're doing over here. Okay. So first, you need to know, you got to calculate the pKa. Ka is provided already. Remember, pKa is negative log Ka. Basically, P means it's a negative log. Like a pH is a negative log of the proton concentration. So pKa, you do the pKa calculation first, is negative log of the Ka. This gives you 4.74. Then you substitute the numbers into the Henderson-Hasselbalch equation. pH will be pKa times log of the base component, which is the acetate, okay, divided by the concentration of the weak acid. This gives you 4.51. as you might have noticed here, the pH you have arrived at is 4.51. This is smaller than that of pKa. This is expected because in this mixture you have a larger amount of acid component than that of the base component. So we just learned how to use Henderson-Hasselbalch equation to predict the relative concentrations for the weak acid component and the weak base component. We also did a simple calculation using Henderson-Hasselbalch equation. Another important concept about a pH buffer is so-called buffer range and buffer capacity. So the buffer range is actually defined by the pKa plus and minus 1. Okay, so do remember, because pH is pKa plus log the base component divided by acid component. Since it's the range, buffer range is plus or minus 1 of pKa, so this also is the same as saying neither concentration should be 10 times larger than the other one. Okay, so neither concentration it should be smaller than or equal to 10 but greater than 1/10. So that's the same. Okay, neither concentration should be too small or too large. The concentration ratio of the two should be between 0.1 and 10. What about buffer capacity? Buffer capacity is the quantity of acid or base that a buffer can neutralize while maintaining the pH within the desired range, which is pKa plus or minus 1. When the initial concentrations of HA and A minus are larger, of course the buffer ability will be larger because it will be able to neutralize more acid or base. Let's look at another calculation based on Henderson-Hasselbalch equation. Determine the number of moles of sodium acetate that must be added to 250.0 milliliter of 0.6 molar acetic acid in order to prepare a pH 4.70 buffer solution, given the Ka for that particular acid. So how do you calculate how much sodium acetate is needed? So we're going to use Henderson-Hasselbalch equation. Okay, remember when you look at the Henderson-Hasselbalch equation, it is pH equals pKa plus log the base component. The base component over here is the acetate, or you can use A minus to represent. The acid component is HA, or the acetic acid. Okay, so basically the concentrations for the acid component, this is known, and Ka is provided, so pKa is also known. pH is 4.7, which is provided. So through this equation you will be able to figure out what the concentration for acetate or A minus is. With that concentration we will be able to figure out number of moles, because concentration times volume will give you moles. So first let's use Henderson-Hasselbalch equation to solve the concentration for the acetate. Okay, all right, so we put down the numbers for the pH and pKa and the concentration for acetic acid over here. So after you do the calculation, you figure out the concentration for acetate is 0.143. The moles is the molarity times volume in liter. 250.0 milliliter is 0.2500 liter. This gives you 0.0358 moles of sodium acetate. In the lab, you can actually figure out how many grams of sodium acetate you have. The moles times molar mass will give you the number of grams of sodium acetate that you need. Then you can measure it out on the balance. Then you can dissolve it into this solution and then make a buffer. Now we're going to switch gear and talk about pH indicators. The pH indicators themselves are actually the weak organic acid, okay? But they are special because they will change color when the pH changes, okay? For example, for so-called phenol red, the pKa is 7.6, okay? The color change will happen when the pH changes from 7.6 minus 1 to 7.6 plus 1, or it's like 1 to 2 units difference. As you can see over here, okay, you have a lot of different kinds of pH indicators, but the color change range is usually 1 to 2 units. Okay, as you can see, change from yellow to blue, red to yellow, okay, red to yellow. You might have yellow to green, etc. Okay, pH indicators can be used to indicate if the reaction is close to completion or not. For example, pH indicators can be used for the acid-base titrations, or sometimes we call this pH titrations. Okay, so basically what you have over here is you have an acid and the base reaction. You try to use the titrations to determine the concentration of one unknown substance. The detailed procedure is, first you assemble a titration apparatus, then accurately transfer the known volume of a sample to a beaker. For example, you could transfer a certain amount of acid. Step 3, you add a few drops of indicator or insert a pH meter, which can also indicate when the reaction is complete. Step 4, you fill the burette with the solution of the known concentration, we call this titrant, okay, to react with the sample that's unknown. We call that analyte. Then you slowly add the titrant with the known concentration until the reaction is complete. Okay, when the reaction is complete, we call this point equivalence point. We have 4 major different types of acid-base titrations. The first type is a strong acid titrated by a strong base. When you titrate a strong acid, like hydrochloric acid, by a strong base like NaOH, the pH in the very beginning is very low because it's HCl to begin with. As you add more and more base to it, the pH slowly increase. Okay, the pH will slowly increase as you see over here. At a certain point of time, the pH will suddenly jump, and then as you keep adding NaOH to it, the pH will increase slightly. So this whole curve, as you see represented in the red curve over here, combined with the purple curve, this is the titration curve for HCl by NaOH. One key feature you need to pay attention to is so-called equivalence point. which is defined when equal amount of acid and base have been mixed up. At this point, everything has been converted to NaCl. As we know, NaCl is the only product at the equivalence point. Okay, since it's NaCl, that's neutral. So at the equivalence point for a strong acid-base titration, pH is 7. We could compare the strong acid titration by strong base with the weak acid titrated by strong base. For example, we use acetic acid titrated by strong base NaOH. In this titration curve, represented by the blue, you start also with lower concentration, but do remember, for the same concentration of the weak acid, because weak acid, the pH you started with is actually higher, okay, higher than HCl. The blue one, which is weak acid, that's the acetic acid. It starts at the low pH area, but this pH you started with is above that of HCl. That's expected for the same concentration as 0.10 strong acid versus the weak acid. The pH initially, you see the quick rise, you see that? This is quick rise. pH actually increase sharply. Remember, when you have the acid to begin with, you add NaOH to it. What happens is a small amount of the acid is consumed. At the same time, it generates small amount of conjugate base. So in the beginning, the acid and base ratio, you have a much larger amount of acid than the conjugate base. So in this region, the quick rise, pH quick rise region, okay, this is not effective pH buffer because the ratio for the acid and base is very large. But while you have more and more acid, weak acid being consumed, you generate more and more conjugate base. So in this range, as you can see over here, in this range, you have the effective buffer, pH buffer being established. That's why the pH increase slowed down. Okay, but as you can see, similarly, as the pH increases, okay, as pH increases over here, okay, at a certain point of time, you also undergo a pH jump. Okay, look at the blue curve. Initially, the pH rises very quickly, then it increases more slowly. Then as you keep adding NaOH to it, the pH suddenly undergoes a pH jump. Okay, at the equivalence point, or when you have same amount of NaOH as that of the weak acid, the equivalence point will have a pH greater than 7 because you generate a basic salt. Okay, so that's several features got to pay attention to. First, you start with the low pH. You see first the quick rise of pH. Then you see the equivalence point pH is greater than 7. Here is 8.73. Right. Let's look at the third type of titration, which is a strong base titrated by a strong acid, as you can see in the blue curve combined with the purple over here. Okay, so if you started with the strong base, the base will have a higher pH. You started with a high pH area, then you keep adding HCl, the pH will decrease at a certain point in time. You will see a pH jump. It significantly decreased, pH decreased then it the rate for pH drop just slows down. Okay, so another feature is the equivalence point for this situation, for the strong base titrated by strong acid. In this case, because you generate NaCl, which is neutral, so in this case the equivalence point for this titration is neutral, or 7, right? Let's look at the last type of titration. If you have a weak base, you started with the weak base, you titrate by a strong acid. For example, you have a weak base like NH3, you titrate it with the HCl, a strong acid. Okay, of course you will also start with high pH area, but do remember, for the same concentration, you look at this, both of them use 0.1 molar. Okay, although both of the concentrations are the same, but for the red curve over here, because it's a weak base, NH3, so you expect the pH you started with to be a little bit lower than that of NaOH. Okay, so it is indeed true, you started with the high pH area, but the pH you started with is relatively lower than that of NaOH. Similarly, we need to pay attention to a couple of features over here. First, look at the red curve combined with the purple. Right, this red curve represents the weak base titrated by a strong acid. In the very beginning, you see the quick drop of the pH, because in the very beginning, some of the weak base is consumed while generating the same amount of conjugated acid. But in this initial stage, you have a much larger amount of weak base than that of the conjugated acid. So an effective pH buffer has not been established initially. That's why you see the pH drop initially quickly. Okay, then the pH drop slows down. At a certain point of time, you see the pH jump. Then after the equivalence point, quickly extra amount of HCl being added, but the pH drop will slow down. Summarize this. For the first feature, pH quickly drop. Second feature, the equivalence point pH for this situation is actually smaller than 7, because you have a strong acid versus a weak base. So if we summarize this about the equivalence point, okay, so if we have a strong acid and the strong base, no matter which one is titrated by the other one, it doesn't matter. So for this case, it's strong versus strong. The equivalence point pH will be 7, because strong versus strong. Okay, what if you have a weak acid versus strong base? See, strong is going to win. So equivalence point pH, we're talking about equivalence point pH, okay, will be favoring the base portion, so pH will be greater than 7. Okay, what if you have the opposite, like you have a weak acid and a weak base with the strong acid? So weak versus strong, strong is going to win. So at equivalence point, your pH will go by the stronger one, which is strong acid. So pH will be smaller than 7. So if we summarize the equivalence point pH, you will be able to see there is a rule. The strong is going to win. If it's strong versus strong, equivalence point pH will be 7. So far, for all the pH titration curves, the 4 different types we have observed over here, they all have one equivalence point and a 1 pH jump. But you can also see multiple equivalence points and multiple pH jumps as well. For example, when you titrate a base like carbonate with an acid, okay, the first step when you do the titration, at the equivalence point, you will have hydrogen carbonate as the product. That's the first equivalence point you observe. Okay. The second step, when you add more and more acid to hydrogen carbonate ion, it will further generate carbonic acid as the final product. That's why you see two equivalence points. The first one here and the second one. 2 pH jump, one and another one. Next, we are going to talk about so-called Lewis acids and bases. We already had some discussions in previous chapter, but now let's use some pictures to have a better idea about what a Lewis acid and a Lewis base is. A Lewis acid is a substance that accepts a lone pair of electrons. So basically, a Lewis acid is electron acceptor. A Lewis base is electron pair donor. Okay. So for example, when we look at ammonia, which usually belongs to Lowry base, okay, but if we look at this reaction of ammonia with water from a different perspective, what really happens in terms of electron is when you look at NH3 Lewis structure, the lone pair that was on nitrogen is picking up one proton, okay, from water molecules. So NH3, when this lone pair picks up that proton, it forms a new bond. So this lone pair picks up that proton, it forms a new bond, NH bond. Okay. So in this process, one pair of electron is being transferred from NH3 to H2O. Okay. So that's what really happened in terms of electron transfer. And when you look at this from that perspective, we say NH3, because it serves as an electron pair donor, we call this Lewis base. And acid, the acid, Lewis acid will be H2O in this case. Let's look at a few more examples. Okay. When you look at the calcium oxide reaction with sulfur dioxide, so this is calcium oxide reacting with sulfur dioxide, which gives you calcium sulfate. So when you look at the picture, here's what really happened. One lone pair of the oxide portion of calcium oxide is donated to the sulfur center. Okay, then it forms a sulfur oxygen bond. Okay. Another example is ammonia reacting with boron trifluoride. Okay, what happens is the lone pair of nitrogen is donated to the boron center. Boron center only has 6 electrons in that Lewis structure, so it forms a bond in between nitrogen and boron. So in this process, you can see ammonia donates a pair of electrons to boron. So in this case, this ammonia is the Lewis base and the BF3 is the Lewis acid. Similarly, the oxide or calcium hydroxide is the Lewis base, and SO2 is the Lewis acid because it accepts a pair of electrons. Previously, we discussed how the strength of an oxyacid depends on the electronegativity of the central atom, shifting electron density away from the oxygen in the OH bond. In a similar way, electrons in the water ligands are attracted toward the positively charged central metal ion, as you see in this picture. For example, in this compound, which is called hexaaqua iron 3 ion, because the iron center is highly charged, so it pulls electron density away from the hydrogen in a successive motion. Okay, so this hydrogen is easily ionized and become hydronium ion, as you can see over here. And in other words, the highly charged iron atoms will combine with water, okay, and cause the solution to be acidic in the mechanism as we just discussed. Okay, so when you dissolve, for example, when you dissolve iron 3 chloride into water and form aqueous solution, you expect this solution to be acidic, as explained by the mechanism in this picture. The iron center is highly charged. It will attract the electron density away from the water molecules that is attached as part of the complex. The relative acidity of the hydrated metal ions is indicated in this table. You notice the acidity will increase, generally speaking, as the charge of the center metal ion increases. For example, this is 3 charged versus 2 charged. 3 charged, they are usually more acidic, as you can see. The Ka's are larger. Let's talk about solubility equilibria. Previously in chapter 14 and chapter 15, we discussed the chemical equilibrium for different chemical reactions, and chapter 15 for the equilibrium for pure acids and bases. Now let's talk about the different types of chemical equilibrium, which is involved with the insoluble salts. For example, when you look at the lead-2 bromide, which is not soluble in water, so we use S to represent a solid. Okay, it's not soluble in water. The salt is not soluble. It just means the solubility is very small. It doesn't mean it does not dissolve at all. Once it dissolves, it will totally, for the portion that has been dissolved, it will totally ionize to the corresponding component cation, lead-2 ion, and the bromide ion. You generate 2 bromide ion. And the solid portion in the equilibrium constant expression is not included. So that's why you only have the products included over here. Okay, SP means it's a solubility product. That's so-called solubility product. It's simply the equilibrium constant, but a special type of equilibrium constant. It's a solubility product. That's why we use KSP to represent it. Use the KSP, we can calculate the solubility for the insoluble salts. For example, find the solubility for PbR2 given the KSP. Okay. How do you solve this problem? First, we build the rice table or the ice table. All right. Do remember, you write the correct equation. Start with the salt, but it's in solid phase because it's insoluble salt. Okay. So it generates the corresponding cation Pb2+. Notice the charge is 2+ over here, and the 2 moles of Br2. Then you build the ice table. Do remember, the solid phase is not included in the KSP representation. Okay, so when you write the KSP, you have the concentration for the cation and the concentration of the anion raised to number 2, because you have a number 2 before that a Br-. Okay, so you substitute the final concentrations in. So it's X times the 2X, the whole thing is squared. Okay. Then you can calculate the solubility, which is 0.0105 molar. That's very small. Okay. So in this case, as you noticed, initially the ions exist in the solution is 0. But in some other cases, you might have a non-zero initial concentrations. In these cases, the calculation is actually easier. When you have one ion on the right side, in this case, we call this common ion effect. Okay, so for example, if you have barium sulfate, which is insoluble salt, you dissolve in water, it generates barium ion and sulfate ion. But if you add some sulfate into it by, for example, by dissolving some sodium sulfate into it. Remember, when you dissolve sodium sulfate, this is a soluble salt. So here it should be AQ, okay? It's a soluble salt. This is a soluble salt. When you dissolve in water, it will ionize 100%. Since sodium sulfate is a soluble salt, everything will be dissolved and ionized. And this will provide an ion which is the same as you see in the first equilibrium. So it's the same ion. We call this ion common ion. According to Le Chatelier's principle, when you add some products to the existing equilibrium, then the reaction or the equilibrium will shift to the left side. This will shift to the left side. Or you will see more solid barium sulfate. In other words, less barium sulfate is dissolved. The solubility is decreased for barium sulfate if you add some sodium sulfate into the solution. And this effect is so-called common ion effect. Another factor will also affect the solubility. That's the pH. And this is called a pH effect. pH decrease or increase in the pH will actually potentially change the concentrations of, for example, the anion F-. In this case, calcium fluoride, which is an insoluble salt, is in equilibrium with calcium ion and the fluoride ion. When you add acid, or in other words, you decrease the pH. When you decrease the pH, what happens is this newly added acid will react with the anion F-, okay, and it generate an acid, which is a weak acid. So when you keep adding acid to it, when you keep adding acid into the solution, it will react with the F- fluoride. This will cause the concentration of F- or fluoride to decrease. So then when you look back to the first equilibrium, the F- concentration is decreasing. According to Le Chatelier's principle, when you have less products, then the reaction will shift to the right side. When it shifts to the right side, that means more reactants will be dissolved, or the solubility, in this case, for calcium fluoride will actually increase. Okay, all right. Let's look at a very similar situation. I'm going to ask you a question. If I change the pH, will this affect the solubility of this compound, calcium nitrate? Will this or not? So when you look at this situation, when you dissolve calcium nitrate into water, okay, it's a soluble salt, it will give you a calcium ion and the nitrate ion. So let's say you add more acid to it, okay, so we're going to just use H+ to represent. So you're going to add more acid to it. Okay, see what's going to happen. So will this acid react with this anion or not? So in other words, will this reaction go to the right side? The answer is no. Because we do know nitric acid over here is a strong acid. The opposite is true. The strong acid will 100% ionize, which means for this reaction, it will go to the left side. It will not go to the right side. Or in other words, no matter how much acid you add to this particular system, it cannot react with the nitrate. Because for this particular reaction, it goes to the left side. So H plus, in this case, will not affect the concentration of NO3 minus or nitrate. In other words, the pH will not have any effect for the solubility of calcium nitrate over here, which is different, okay? Because nitric acid is a strong acid. But so we look back. For calcium fluoride, when you decrease the pH, the solubility for calcium fluoride will actually increase. The reason is because the addition for the acid, okay, the addition for the acid can cause the equilibrium of F minus reacting with H plus to the right side. This will decrease the concentration of F minus because you have the second equilibrium over here, because HF is a weak acid, so the reaction will happen both ways. However, for the nitric acid, it's different, because nitric acid is actually a strong acid. The reaction, no matter how much H plus you add, this reaction will not go to the right side. Rather, it will go to the left side 100%, because nitric acid is a strong acid. So the conclusion for pH effect for calcium fluoride and the solubility for calcium nitrate is totally different. If you decrease the pH for CaF2 solution, then the solubility for CaF2 will actually increase. But for calcium nitrate, the pH will have no effect on its solubility. All right. Okay. So that's so-called two factors affecting the solubility. The first one is the common ion effect, which is easy to understand because the common ion increases the product concentration, cause the reaction to shift to the left side. So more solid is being generated, so the solubility is decreased. The second effect, pH effect. Right. Okay. So let's do some calculation based on the common ion effect. So calculate the molar solubility for the same salt, PbBr2 or lead-2 bromide. Okay, but the difference is now not only you have an insoluble salt, you also have a soluble salt over here. How do we know calcium bromide is soluble? In General Chemistry 1, when we talked about the solution phase, we talked about the solubility rules. But even if you don't remember those solubility rules, first it will be provided in your exam. Even if it's not provided, you should still know, because only KSP, when you look at that, only KSP for the insoluble salt is provided. The one, calcium bromide, has no KSP indicated. So this hints that calcium bromide is soluble. Okay, so when you build the rice table for this particular equation, it's the equilibrium for the insoluble salt, because the soluble salt has already dissolved and ionized 100%. So if you have 0.20 molar CaBr2, when you can actually write that, but it's not equilibrium. So this will actually ionize to Ca2 plus and the 2Br minus. That's no equilibrium, it's 100% ionized. So for each CaBr2, you will generate twice as much Br minus. So that's why the initial concentration for Br2 is twice as much of 0.2. That's 0.40. That's why the initial concentration here is not 0. It's 0.40. So you build the ice table, initial concentration for the lead-2 ion 0, and you do plus X over here. That's plus X, and then you have plus 2X. The reason is because you have a 2 Br minus over here. So for each X, you have a 2X being generated because the ratio is 1 to 2. 1 to 2 ratio. That's why here is 1X, here's 2X. Okay, now you solve for this KSP expression. So you substitute the equilibrium concentrations in. This gives you KSP equals X times parenthesis 0.40 plus 2X squared. Okay, as you notice, the KSP over here is very, very small. Okay, so we can use the small x approximation, which means 0.40 plus this 2x, because the reaction will barely go to the right side. So 2x compared to the initial 0.40 is small. So 0.40 plus 2x is about the same as 0.40. So you substitute this into the KSP expression. KSP, so it's about the same as x times 0.40 squared. Don't forget about that squared. That squared is still there. So you keep that squared. Okay. So the calculation for x is actually a little bit easier. This gives you 2.92 times 10 raised to negative 5 molar. Indeed, that x, or the solubility, is very, very small. We have one more topic before we conclude this chapter. In chapter 14, we learned one key criteria to judge whether the reaction is at equilibrium or to which direction the reaction will shift to, by looking at the relative magnitude of reaction quotient Q, compare that with K, equilibrium constant. And we have learned if Q or the reaction quotient is smaller than K, right, the reaction will proceed to the right side. Remember Q, if you still recall, Q and K takes exact the same form, but the meaning is different. Okay, Q is all current concentrations ratio, the product over the top and the reactants at the bottom. Okay, K takes exact the same format, but all the concentrations or partial pressures will refer to the equilibrium concentrations or partial pressures. Okay, so let's look at one example, see how we can use this Q and K relative magnitude to judge the precipitation reaction. Okay, so let's look at this reaction. So we do know lead-2 chloride, or PbCO2, is an insoluble salt. So if I mixed up a certain amount of lead-2 ion with chloride ion, I want you to tell me if you expect to see a solid, or so-called a precipitate, to come out. Okay, so what you can do is, first you got to know how to write the equilibrium expression according to the correct ionization equation. Okay, so you write out the correct ionization equation. You do know what the KSP is. Okay, that's the K. Your Q is taking exact the same format of K. That means the concentration of PbR2, okay, times the concentration of a Cl minus, because you have a 2 chemical coefficient before Cl minus. That's why you raise it to 2. Okay, substitute the current concentration in for Q, then you find out what the Q value is. You compare Q and K, you find that Q is smaller than K, which means the reaction will actually shift to the right side. So when you look at this reaction over here, because Q is smaller than K for this reaction, okay, Q is smaller than K for this reaction, That means any solid over here will keep being dissolved because the reaction will shift to the right side, or you will not see a solid being formed, so no precipitate for this situation. All right. Okay, that's it for today. Have a good day. Bye.